welcome back to page 12. Number 57, complete the chart. Now notice we're talking about the sum of interior angles. So before we get started, let's keep focused on what our formula is to find the sum of interior angles. And the formula is S for sum equals 180 times the number of sides n minus 2. Now we have 4 different examples here. For the first one, the list is nonagon. So the number of sides is 9 for a nonagon. To find the sum of interior angles, we're going to do 180 times 7. N minus 2 is 9 minus 2, which is 7. So 180 times 7 equals, in the calculator, 180 times 7. 1260, so 1,260. The next one, 14 sides. Now, there is a fancy name for it, but I don't really use it. Instead, I call it a 14gon. Any number of sides above 12, I usually call it by the number of sides, then a dash, and then the word gon, or the little piece of a word, gon. So 14 dash gon. Okay, so again, we're going to do 180 times, we're going to do n minus 2, which is 12, so 180 times 12. Always 2 less than the number of sides. So 180 times 12. In the calculator, let's go ahead and do that. 180 times 12 equals 2,160. All right, moving on. A decagon. Like the word decade. There's 10 years in a decade, so a decagon has 10 sides. So you're going to do 180 times 8. 180 times 8 equals 180 times 8 in our calculator. We get 1,440. All right, now the last one is a little bit different. They didn't tell you what type of polygon or the number of sides that you have. Instead, they gave you the sum of interior angles. So you have to work backwards and figure out the number of sides. Now let's use our formula. Sum equals 180 times n minus 2. And let's go ahead and plug in this 4320 as our sum, our S. 4320. And we're going to work backwards to solve for the number of sides. Instead of distributing, which I can absolutely do, I'm going to instead divide both sides by 180 so that I can free up the parentheses. So in my calculator, 4,320 divided by 180. So it's 24 for n minus 2. 24 equals n minus 2. I freed up the parentheses. Now n minus 2 stands for the number of triangles that will be inside of your polygon. So there's 24 triangles that fit into my shape, but that's not the number of sides. I need to add the 2 back, and instead we get 26 equals n. So it's a 26-sided polygon, 26. So I'm going to call it a 26gon. Okay, so if you're ever given the sum of interior angles and you're trying to figure out the number of sides, just go ahead and use that same formula, but plug in for S and work backwards. Use your algebra, solve for n. Okay, let's keep it moving. Number 58. Determine the smallest degree of rotation that will carry the regular octagon onto itself. Okay, so we're looking for the smallest degree of rotation, also known as the increment of rotation, that will carry the octagon onto itself. It's important that they told us this is a regular octagon. If it wasn't regular, we wouldn't be able to do what we're about to do. And for the octagon, that means we have 8 sides. So when we rotate, we always rotate around the center of our polygon. Now, the amount that we rotate is equivalent to the central angle of your polygon. So we form our central angles by drawing well, that's not a good line, so let me fix that. By drawing the 2 radii to your polygon. And the angle right here is your central angle. So to figure that out, we always do 360 divided by the number of sides. In this case, it's 360 divided by 8. In your calculator, 360 divided by 8 is 45 degrees. So that means I can I can rotate this figure 45 degrees, either clockwise or counterclockwise, and it will map onto itself, meaning it will look like it hasn't even moved. So I can go clockwise, or I can go the other direction, 45 degrees. Now, not only will you go 45, but you can go any increment of 45. So that means 45 plus 45 is 90. So I can rotate it 90, and then this corner here, or this vertice, will map here if it's 45, here if it's 90. And if we keep going, we're going to go to the next vertice, and the next one, and the next one, and the next one, and the next one, until we're back to the beginning. Now, we're always rotating around our center point when we're rotating. So make sure you understand that when you map some polygon onto itself and you're doing a rotation, you should rotate around the center point, which we'll look at for the next problem. Now let's keep going. Not only can we go 90, if we add another 45, we're at 135 degrees. Another 45, we're at 180. So this figure will look like it's upside down. Keep going for another 45, we're at 225. Another 45 gets us to 270. Another 45 gets us to 315. And then one more 45 gets us to 360. Now notice how many rotations this was. This is 1, 2, 3, 4, 5, 6, 7, 8. The order is 8. And order means how many rotations of this 45 degrees will get this figure back to where it started. So the order is 8. You can do 45 degree rotations, little 45 degree rotations, 8 times to get this figure to go right back to the beginning. But any of these amounts will make it look like it mapped onto itself. It'll look like it hasn't moved, as long as it rotates around the center. So that was a lot of additional explanation, but really all I wanted to know was this piece right here. I added all that stuff in to help us with the next question. So I'm going to write down my final answer here is 45. All right, let's keep moving on to our next question, number 59. Number 59. Which of the following rotations will map the regular polygon shown centered at 2, 3 onto itself? Select all that apply. So the center of this shape is at 2, 3. That's this point right here. So they're asking, well, how can we rotate this so that it maps onto itself, so that it looks like it hasn't even moved? Now remember, when we figure out our angle of rotation, our increment, we do what we did in the last problem. 360 divided by the number of sides. Since it's an octagon, we can count the number of sides. It's an octagon, we divide by 8. And that gives us 45 degrees. So any increment of 45 will work. So let's list out all those increments again, just like we did with the last problem. 45, 90, 135, 180, 225, 270, 315, and 360. Now the key is that we're rotating any of these amounts, but also that we're rotating around the center of the polygon, which is at 2, 3. So if we're not rotating around the center, it's not going to work. But there is one exception, and we're going to go ahead and look at it. So the first choice says it's a rotational amount of 360, which I'm happy with. 360, that's going to work. Centered at the origin. So the center is not at 2, 3. However, you can always rotate 360 around any point. That's the one exception to the rule. If it's 360, it could be any point. It does not have to be the center. So the fact that they listed the origin, yes, absolutely. It could also have been the point 1,5 or -7,4. It literally could have been any point if it's 360. So I'm going to go ahead and check it off. The next one, again, notice it's 360. So really, it doesn't even matter what center they list. But they listed 2, 3, which is our center. So I'm happy with choice as well. Next one, rotation amount of 90. So let's take a look, 90. Is that on our list? Yep. So I'm good with that. But look at the center. The center is at 3, 5. I can only rotate around 2, 3, not 3, 5. So no. Next one, a rotation of 45 degrees. Yep, 45 is on my list. That's actually the smallest amount that you can rotate. And they have us rotating around 2, 3. Perfect. That will work. Next one, a rotation of 225. Let's check if that's on our list. Absolutely, it's on our list. But centered at the origin. No. If it's any number other than 360, it has to be around the center 2, 3, the center of the polygon. So no. Next one, a rotation of 270. Yes, that's on our list. Centered at 2, 3. Perfect. Last one, a rotation of 181. That is not on our list. 180 is, but not 181. Nope, not going to work. Even though it is centered at 2, 3, it's not an increment of 45 degrees. So no. So these 4 are our correct choices. Let's move on. Number 60. Find the value of x for the equilateral triangle. Now, equilateral means all the sides are congruent. They're all the same length. It also means that it's going to be angular, meaning all the angles are going to be the same measurements. In this case, all the angles are always going to be 60 degrees if it's an equilateral triangle. But what we're looking at is not lengths, what we're looking at is not angles, but we're looking at lengths of sides. So don't even focus on the fact that it's equiangular. Focus on the lengths. Since all 3 are given, you only need to pick 2 at a time. So it doesn't matter which 2 you pick 2 at a time and you set them equal. I'm going to pick the x plus 13 on the left and the 3x minus 1 on the bottom. It's just a choice. You can pick any 2. So I'm going to go ahead and set them equal to each other because they should have the same length. That's why it says equilateral. And I'm going to say x plus 13 is equal to 3x minus 1. I always work with the x's first, so subtract x from both sides. We get 13 equals 2x minus 1. Add 1 to both sides. So 14 equals 2x. Divide by 2, and we get 7 equals x. 7. Now, watch what would happen if I plugged it in. If I did 3 times 7 minus 1, 3 times 7 is 21, minus 1, I get 20 feet. If I look at the left side, 7 plus 13, again, 20 feet.
7 plus 13 is 20.
And the last one, 6 times 7 minus 22. 6 times 7 is 42. Minus 22, I get 20 feet. So notice all 3 lengths are the same. It would not have mattered which 2 I picked to set equal, but x is 7. Let's go ahead and move on. Number 61. Use the accompanying diagram to answer part A and B. Part A, what is the perimeter of the parallelogram? Round to the nearest hundredth. Okay, perimeter. We need to get all the side lengths. So we have 4 side lengths for this perimeter. So I'm going to put a blank for all 4 sides to keep myself focused on what I need. Now let's take a look at our side lengths. The top and bottom are congruent because it's a parallelogram. So the top and bottom here are going to be very easy to find since they're horizontal lines. So all you need to do is count the boxes. So we have 1, 2, 3, 4, 5, 6, 7 for the length of the top, which means that the bottom is also going to be 7. So I'm going to go ahead and put in that I have 7 and 7 for 2 out of the 4 sides. Now the left and the right sides are going to be equal as well. However, these two are slanted. So to find their lengths, I'm going to have to either do distance formula, which you know I'm not a fan of, or the Pythagorean Theorem, which, as you know, I do it all the time. So let's go ahead and do the Pythagorean Theorem. Remember, go ahead and draw your little right triangle. We're going to count our boxes vertically. 1, 2, 3, 4. That's the height of this triangle and also the height of the parallelogram. But here we have 4 squared plus horizontally, it's just one box. So 1 squared equals the c squared. 4 squared is 16 plus 1. 16 plus 1 is 17. We square root that at the end in order to get c. So I have square root of 17 for one side on the left, and the right's going to be the same thing because it's a parallelogram, and opposite sides are always congruent. So I'm going to use my calculator to add all of these up. So in the calculator, we're going to do 7 plus 7 plus 17 square rooted, which is about 4.1, plus 17 square rooted equals. So in total, it's about 22.46 if I round to the nearest hundredth, like it's asking me to do. So that's my perimeter. Next, what is the area of the parallelogram? Now, area of parallelogram is the same as the area of the rectangle. Base times height. The key is that when you're doing base times height, you use a perpendicular height. Okay, it has to be the official perpendicular height, the altitude of your shape. So in this shape, I just need to go ahead and figure out, well, how tall is my parallelogram so that it's perpendicular to your base of 7. So if I go ahead and count that, it's 1, 2, 3, 4 units tall. 4 is my height. 7 would be my base. So I'm going to go ahead and multiply for area. Base of 7 times 4. Area equals 28. So my answer here is 28. If they ask me for units, and just so that we are refreshing our memory, if it's area, it's 28 units squared. For the perimeter, it's a length. It's a length of the outline. So it's just going to be regular units. Okay, and that completes our page. Let's move on.